it all works. And then we come to our book, get our book going. Now our book is the DC and then the AC book under Fiore. So if you haven't looked these books up or loaded these books, these are free books. And this is in the website. And we're going to go down to chapter 9 and work a few problems today on inductors. And by the way, I have to leave a little early. Not a lot early, but just a little bit early. And I can't stay around afterwards for questions because I got a meeting at 9:30 and I got to be there on time. So my apologies for that. Usually afterwards, after class, that type of thing, we got a little bit of time to discuss and decide what's going on and all that kind of thing. But today it's a little bit different, and I'll just have to grunt and groan and bear it today. So anyway, that's what it is. So anyway, we've got some problems in chapter 9. We're going to work, and we're going to try to get through these today. And we're going to get on to chapter 10, which chapter 10 is hate to say it, but it's kind of a fluff chapter. If you like easy chapters, chapter 10 is easy. I just basically take it as a chapter and say, this is an easy chapter. Don't try to put any more into it than you absolutely have to. And we get through it. And we don't try to understand everything about transformers at that point in time. There's a lot more that you can understand about them, but we try to make it straightforward and what you need to know in order to get through that. So that's all that chapter 10 is. It's a very simple chapter. So these 3 chapters, 8, 9, and 10, at the end of this DC book, you probably have already done, and we're not trying to impress you with our ability to do them again, but at least I want you to get through some of these problems and understand them, and then we go on. There are a couple of problems that were assigned. It's on the syllabus, and I forget which ones they are right now. We'll probably work through those. Forget what they are, but they're on the syllabus. You owe me those problems. You owe me the problems. That there are 2 problems in chapter 8 and a couple problems at the end of chapter 9 that you owe me, and we'll go back and look at the syllabus. Try to before the end of the class. Okay, the problems that are on the syllabus, you owe me, all right? They're not a lot, but there are a few. All right, so how do you combine inductors? Like if you had 2 of them, you just add them together if they're in series, right? So this would be what? Number 1 would be what? That's 6 millihenry, right? All right, any questions about that? Number 2, how do you do that one? Well, it's the same thing. They're in series, so you just add them. Now here they play the game with you a little bit where you've got some milli and some micro, and that's 10 to the minus 6th. So it's 2 millihenries plus 1 millihenry plus 0.6 millihenries. Do everybody understand that 600 microhenries is 0.6 millihenries? 600 times 10 to the minus 6 is equal to 0.6 times 10 to the minus 3. Any questions? Does that make sense? All right, so that's why you do that. So what do you get? 3.6 millihenries. So that's that one. Okay, any questions so far? What about this one? They're in parallel, so use the parallel rule. 1 over 3 plus 1 over 1 is equal to what? Well, we have to take our calculator out and do that one. And does anybody have the answer? Pardon? 0.75 sounds about right. 0.75 millihenries. Any questions about that one? It's the 1 over 1 over rule. Or this one times this one over this one plus this one. Here it's a combination. And it's 2 plus what? 2 millihenries plus 4 times 1 over 4 plus 1 is 4/5, or 0.8. It's 2.8 millihenries. So far, so good. Okay, now This one is determine initial voltage across each component of the circuit shown in the figure below. Now we have to go with, here is startup condition or initial conditions, okay? So with a capacitor, when it started up, the capacitor initial conditions was what? A short circuit. What would be the initial conditions for an inductor? Yeah, it's just the opposite, open. Okay, final conditions for a capacitor are a final conditions. Open. Final conditions for an inductor. Closed. So here we have, and I get these confused. I sometimes saying backwards, but that's exactly what it should be. Okay, so here, what do we have? Number 5. Initial conditions for, and it says, what are the initial conditions? So you have to look at the initial conditions. Okay, so initial conditions for, so I have 10 volts. That doesn't change. The 2K doesn't change. Now the capacitor is a what? Short. And the inductor is an open. Now we've got a resistor over here. We've got a resistor up here. What's the voltage across that circuit? Did everybody see what I just did? I redrew it. So what's the voltage across the 2K? It's voltage divider. See how voltage divider is so important? And when you were learning this in resistive circuits, you said, another rule to learn. You use it again and again and again. So here, we use it here. It's 10. Voltage across the 2K is what? 2 over 2 plus 4 times 10. Or what? 3.33 volts. Now, what's the voltage across the 4K? It's what's left. So you go around this loop, has to add up to 10. It's 6.67 volts. Now, what's the voltage across the inductor? What's the voltage across the inductor? What's the voltage across here? Well, the voltage across here is 0. It has to add to what? This is 6.67. So the initial condition of voltage across the inductor is equal to 6.67 volts. The initial voltage is 6.67 volts. Does everybody understand that? So it's kind of, you work backwards, right? And this is just a snapshot in time. This is not forever. This is just, when I said ready, set, go, it's when it turn it on. In other words, when you turn the 10 volt supply on, that instant, it pops this, and then it changes. But it doesn't, it changes to some new value. And that new value you're going to have to find out. You can't solve this problem in this course. Why not? That's the second order differential equation. Because you've got R's, you've got L's, and you've got C's, and you've got DC. Now, the good thing about AC circuits is you can solve these problems in AC land, but you can't solve them in DC land because it's not initial condition circuits that we're talking about. We're talking about in AC land, we're talking about steady state. What is steady state? It's after a while, after you've turned the circuit on and you've let it run for a while, the steady state conditions you can solve. And in most cases, AC state, steady state is all you need in order to calculate your currents in AC. You don't worry about transients. You just let it go, let it rip. Okay, number 6. Determine a steady state cost for each component. Now we got to do the opposite, right? So now we draw the circuit with its exact backwards. So number 6, everybody follow that? So number 5 is this way. Number 6 is, are you telling me that you got to redraw this thing again? Yes, you got to redraw it again. Here's my 2K up here. Here is my inductor, and it is now shorted. Here is my capacitor, and it is now opened. Okay, so what's the voltage across each of these components, right? What's the voltage across the 2K resistor? 10 volts. What's the voltage across the 4K? What's the voltage across here? Any questions? That's it. You say, so I can find initial and final conditions, but I can't write the equation. That's correct. You can't write the equation yet. We're practicing for the day that you can, but you can't do it yet. You have to wait till EET 3250. So we're getting you prepped, but can't go there because it's too many balls in the air for right now. Anyway, that's that. That's okay. No problem. Given the network of 941, determine the steady state voltage across each component. Steady state voltage across each component here is what? So number 7, now they're asking for the steady state, and then they're asking for the initial. So do we want to solve number 7 first, or do we want to solve number 8 first? Do you care? Are you awake? Do you want to go number 7 or number 8 first? Do you want to do initial conditions? Because that's problem number 8. Initial conditions and then final conditions. Let's do number 8 first, okay? So let's just ask the question. The circuit, this is the problem. This is number 8. Here's my circuit, okay? Here is my 2K resistor, same old, same old. Now I've got a capacitor here, and I've got an inductor up here, and then I've got resistor down here. So basically, what did they do? He just moved the two around, didn't he? That's all he did, right? So here it is, same circuit, same song, second verse. 10 volts, 2K, 5 microfarads, and 3 millihenries, and 4K over here. All right, so number 8, initial conditions. X like 8, capacitor, X like 8, what? Short, right? And the inductor, X like N, open. So we have the exact opposite. We have exactly what we had before, which is what? So number 8 is just like number 6. Here's my 2K up here. Short, nothing, 10 volts, 10 volts. All right, so number 7 is what? Final conditions. Final conditions are what? And by the way, I can mess these up with the best of them. So if somebody says you just said it backwards, you know, I can, and I know that I can. So I have to be very careful when I do these, because after a while, if I think about them, I say, oh, yeah, you did it backwards, Ted. But I am prone to put these in backwards. So if you haven't figured it out yet, I can make mistakes. So again, 2K and 4K splits like it did before. So number 7 is like number 5, number 8 is like number 6, and we're done. Any questions about this? Piece of cake. Yeah, it is. Not a hard thing. Again, please take your crib sheet that you're building as you go through this course and make sure that you write these 2 things down about the open and the close of a capacitor and inductor, because it is confusing. And just make a little notation. Initial conditions, final conditions, capacitor and inductor, open and closed, and you should be okay. And just apply that. Number 10 is another one, and number 11 and number 12 are another one. Okay, so we're going to skip through those. want to get down to, let me see here, number 15. Okay, so this one is determining inductor current 20 microseconds after the switch is turned on. So at 20 microseconds after the switch is turned on, assume this is an inductor and there's no internal resistance. That's a big assumption because there's always internal resistance, but let's just pretend, okay? So here is the issue. So we've got number 15. We have ice, and a lot of it today, and we have Eli. So voltage is equal to L derivative of I with respect to t. So this is the slope of I over t. So now we have a picture here of voltage, which is 10. So the slope of this line is going to be V over L. So it's going to be 10 over 1 times 10 to the minus third. So the slope of this line is equal to 10 to the fourth. So this is the 1 times 10 to the fourth is the slope. All right. So if you have the slope of a line that goes through 0, all right, you can say the output, which is this. This is my output. This is my input. Y equals mx plus b, right? Y equals mx plus b, always. What is m? M is the slope. So the output voltage at a certain instant in time is equal to 10 to the fourth times t. Everybody follow that? Now, what is t? 20 microseconds. What is microseconds? 20 times 10 to the minus 6. So my voltage at 10 to the fourth times 20 times 10 to the minus 6 is what? It's 20. I give you that. Times 10 to the minus 2, or 2 times 10 to the minus 3, right? Right? No, it's 200. 20 times 10 to the minus 2 is 200. Times 10 to the minus 3, or 200 millivolts. Went the wrong way. Okay, 20 times 10 to the minus 2 is 200 times 10 to the minus 3, right? Everybody agree with that? Or 200 millivolts. Okay, that's that one. Now, will I ever ask that question on a test or again? I don't know. I have, but again, that's a good question to know. So how did I get there? I recognize that the voltage over L, V over L, is the slope of that line, which comes straight from the differential equation, which we don't ever talk about because this is supposed to be an algebraic only course, but we have to. We're talking about algebraic things, but we're also talking about some calculus things. When I say d, that means the derivative of or the slope of. That's all it is. That's it. That's all we do for that one. Number 15. Okay, now 16. Let's do number 16. How would you do this one? How would you do this one? Same thing. All right. So number 16 is the same as number 15. ICE, E-L-I. If you can remember that, you're in, okay? Basically, you don't have to remember a lot in electrical circuits, just a few things, but Eli and ICE are two that you need to remember. And I do it this way, it's E-L-I, I write E-L-I, then I write voltage, because voltage and E are the same thing, so V is equal to L di over dt, all right? And then I say, Okay, this is the slope of I with respect to time. So basically, um, I worked that backwards. I said voltage, and it was that last one I said voltage, and it was current. This up here is I, not V. Sorry about that. I did it wrong. I told you I'm messing these up, and I did. It's I versus T, and that's V over L is dI over dt. So dI over dt is the slope, and this is I, and this is T. I'm sorry about that last one. I did it wrong. But now we've got it. Okay, so they asked for the inductor current, and I solved it for voltage. It should have been milliamps. Okay, same thing. I messed it up. But now we're okay. Everybody got it? The last one was instead of voltage, it was current on this axis. All right, so now either you were asleep or you're just letting me ramble on, but basically I was wrong. This is what we should have been doing. This is the conductor current. The I over dt is this term right here. So slope, voltage, okay. So you got volts, 50. And what is L? 2 times 10 to the minus 6th. So now what is the slope? It's 25 times 10 to the 6th. So this slope here is 25 times 10 to the 6th is equal to di. This is a quick one. All right. Does everybody see how when these get small, time goes quick? And that's exactly the case. If you get a big inductor, you go slower in time. If you get a small inductor, it's faster. All right. Okay, again, no internal resistance, and that's a big step, but that's what they basically want you to buy into. Okay, so now we solve this. We say y, or I, equals 25 times 10 to the 6th times t. And they give you a time, 100 milliseconds. So it's 25 times 10 to the 6th times 100 times 10 to the minus 3rd. And this is going to be a big one. It's going to be a large current. And again, it can't be because this is, there's a resistance. There has to be resistance in these circuits. This will not take off and run. Okay, so let's just see what this is. 25 times 100 is 2500 times 10 to the 3rd. That's a big current. That's a whopping big current, and that cannot be sustained by this. So this will never work, but that's the theory of this, how it's supposed to work. There's resistance in this circuit, okay? All right, so anyway, am I right? Did I mess up someplace? 2 microhenries, 50 over 2 times 10 to the minus 6 is 25 times 10 to the 6th. Yeah, that's it. That is a lot of current. Can't be, but that's the theory of how it's supposed to work. Okay. Again, there's internal resistance in the circuit, and it will never get there, ever. But this will not support that kind of current. All right. But it just proves that if you lower the, if you can play with numbers that you can't actually build in the real world. Anyway. All right. Enough on that. But other than the fact that I messed up the other one, this is how you do that. You find the slope, and then you say y equals mx plus b. M is the slope. Any questions so far? Other than the fact that I messed up? All right, so now we get into the what? Now we get into the fun part of this. This is the fun part of this whole thing, and that is that we get to look at a circuit that turns on or turns off with an inductor, and we see the decay or the rise, and it's either this 1 minus e to the minus t over tau, where tau is equal to L over R, or it is e to the minus t over tau, where tau is equal to L over R. Now, which one is which? Is this the charging and this the discharging, or is it vice versa? This is the charging. This is the charging circuit. This is the discharge. And we're now talking about I instead of V, all right? Other than that, same thing as we talked about with voltage. So that's the similarities between voltage and capacitance and current and inductors, okay? So if you get it in your head that, yeah, voltage is, okay, a capacitor is a storage device for voltage. Current is a storage device for inductors. You've got it. And then Eli and ice and you're in, kind of. And this little thing right here. So you've got this E and 1 minus E, and then tau is, in the case of a capacitor, it's RC. In the case of an inductor, it's L over R. And that's it. And because you only have either an L or a C and an R and a V, you can write these. If you have both L's, R's, and C's in a circuit, you can't write these, okay? You have to go to differential equations, and you have to go to Laplace transform, you have to do all that stuff in order to find out the answer. In this course, right here, you're in with just this. So this is kind of a first step, okay? Now, in your studies and all that kind of stuff, that probably doesn't matter to you very much, but they kind of go first order differential equations are the freshman, sophomore, maybe junior level stuff, and then the senior level stuff is, or junior and senior level stuff is the second order differential equation. So basically they kind of separate the two out. So this is supposed to be, I could teach you the second order differential equation stuff right now, and you could probably get it. But we kind of hold off a little bit and we say, you got to understand this before you can understand that. So that's kind of why we're holding off a little bit. I don't want to apologize for it, but that's exactly what we're doing. We're saying we're going so far and we're going to go further with the other one. Okay, so basically this is in what? AC land or DC land? There's a room for AC stuff and there's a room for DC stuff, okay? This is the DC room, okay? Why is it the DC room? Why are we in the DC rules room? Because of that right there. If we change that to a circle and put a little squiggle in it, that means it's an AC circuit. All right, so you're looking for a battery, okay? So put your detective hat on and your spyglass, and you start looking out. Is he asking for a DC circuit or an AC circuit? And I'll ask you a question on a test, and I'm going to put either that or that in, and daggone it, some of you are going to go this way and instead of this way, okay? Why? Because you didn't take that into account, which way it went, okay? So there are different rules for different rooms, all right? This is the DC room. That's why I'm going back and doing it again, because I want you to understand that we're going into the second part of this course, which is the AC room. Right now we're in the DC room. So I want you to get this, there's a big wall here, right? The rules for the DC room are E, something with E. Right? Everybody got that? The DC room is something with E. What is E? We don't really know yet. Maybe know a little bit, but what is E? 2.71, right? Something like that. It's just a number. It's also a function on your calculator. You get an answer from, right? But it's just a number, all right? But it also explains what? Why things don't go immediately. Why they dribble or why they take time to when you open you get one of these things with water in it and it's got a spigot at the bottom. You open the spigot and just let it drain out. It doesn't just drain out and then done, right? It doesn't whoop done. It's not a square wave. It starts and it gradually, it actually slows down as it goes to the end, right? It does slow down. That's a first order differential equation. That's explaining this E thing. And we're going to do this in lab. We're going to actually time out, and we're going to actually get this little. Get your stopwatch. You have to have a watch. You have to have a calculator. You have to have You have to have a phone that's got time on it. Every 10 seconds you mark off, there it goes. And that's it. But you got to be in the right room. You got to be in the right. You have to look at these and say, now, which room am I in? Because I'm going to give you, I'm not going to tell you, you're in the DC room or you're in the AC room. I'm just going to put the little circle, and that's it. I get off my soapbox. But I do care, and I do want you to understand that you have to watch. You have to look and see which way it is. And if you take off down the wrong path, it's a 10-point question. It's minus 10, minus 9. I hate that because you might solve it the right way. You might solve it. The problem is they look the same except for that. We're not trying to trick you. It's just, ugh. Okay, enough. So now we're down to the good stuff. This is the good stuff. Okay, so we're now down to number 17, which is the good stuff. Okay, so let's do this. So we close this switch, and we usually don't close a switch, we close a what? When we close this is symbolic of a quick-acting transistor, or it's just a transistor, okay? That really, we don't show that, but that's what that is. It's a transistor that closes a circuit, and then it does it, okay? So in this case, we're asking for the time constant and the time to right steady state for the current below. So now we're asking for the equation for what? So he doesn't even say it, but it's the current, right? So for voltage, for capacitors, you solve for voltage. For inductors, you solve for current. So 17, you're going to say I through the capacitor is equal to what? 12 over 25, which is this over this, times what? 1 minus e to the minus t over tau, where tau is equal to L over R. What is L? Tau is equal to 500 times 10 to the minus third over 25, which is equal to what? 20, right? Any questions so far? So I can write this equation. Now see what he says. Determine the time constant and the time required to reach steady state for the circuit. Now, why are they saying the time constant? Why are they asking that? Okay, so it reaches steady state. If you do this equation and you do it minus 5, e to the minus 5, you get, or it's less than 0.01. Okay? But you consider 99% steady states. So e to the minus 5, so if you said 5 tau, you have reached steady state. You've reached its final destination. So what would be this tau? What's 5 tau? Is 100 milliseconds, right? These are seconds. Tau is time. So 5 tau is about steady state. So that's the answer to that question. All right. Now here is the rub. Excuse me. Now this is no, that's all they say in 17. Just find that, and you're done. Okay. Now we get more into this as we go down the list, though. Now number 2. Oh, and by the way, what is this circuit up here? If you cut off the inductor, what would you have? You would have a Thevenin circuit, right? Why is it a Thevenin circuit? Because you got a voltage and you got a resistor and you got a voltage and that's it, and you got an open circuit. So if I took it and I snip right there, that's what you would have, and that's a Thevenin equivalent circuit. So in essence, what you have to do is you have to reduce this part of it, including that switch. That switch really is just pretended it's closed, okay? Just wire through it, draw a line through it, and say, okay, we're understanding that at time t equals 0, this thing turns on, and that's why this turns on right now. It says go at time t equals 0. What is this if time is negative? We don't care, because this is only, there's a second part to this equation at t greater than or equal to 0, okay? So if t is less than 0, this thing does not exist. We have to put in there. Not only this, but we have to put in this caveat, because at t equals negative numbers, we don't let that happen. We don't let that negative number, because what would happen then? We would have a big, whopping big number. If you say e with a plus number, if t is minus, then you got a plus number here, and you got a big, 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 big number. E to the minus number goes down quickly. It falls away, and then it kind of levels out. But if you say t is a negative number, then daggone it, you just basically made yourself into a whooping big number, exponential rise. It's not a good thing. Okay, that's that. Now, the second one, this 18 down here, asks the same question, but it's just a little different. What do they ask? A time constant, a time required, blah, 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 and all that kind of stuff. Now, given a circuit, determine voltage, blah, 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 all that kind of stuff. Okay, now here, this is a typo, because it should say 947. Okay, so this is the part that I really want to get at. So here, in number 19, determine the inductor voltage and current 200 milliseconds and then 2 seconds after the switch is thrown. Okay, so determine the inductor voltage and circulating current. So here, so number 17, okay, so number 17, our I is equal to 12 over 25, 1 minus e to the minus t over tau, where tau is equal to L 500 times 10 to minus third over R, which is 25, or we've got 20 times 10 to the minus third. So that's my tau. Okay, so now they ask the current. What is the current 200 milliseconds or 200 milliseconds afterwards? So basically it's equal to number 19, and that's a typo. It says 937, it should be 947. It's 12 over 25, 1 minus e to the minus what? 200 milliseconds. So it's minus 200 milliseconds over 20 milliseconds. What is that? It's minus 10, right? AI assistant, daggone them. Determine inductor voltage and circulating current 200 milliseconds and 2 seconds after the switch is turned. So basically, he is saying 200 milliseconds at e to the minus 10. So basically, what is the voltage at 200 milliseconds? What is I equals? What is e to the minus 10? Everybody find out. Very small, very, 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 very small number, okay? I think he wanted to say at 20. I think he really wanted to say at 20 milliseconds instead of 200 milliseconds. So let's just do it at, let's just pretend that he had a typo here and a typo here, and he really wanted it at 20 milliseconds. Okay? So let's just pretend that he is at 20 milliseconds. I equals what? 12 over 25, 1 minus e to the minus 1. What would that be? Okay, so that this part right here, 1 minus e to the minus 1 is 0.632. All right? And that 0.632 times 12 divided by 25. 12 divided by 25. Divided by 25 times 0.632 equals 0.308. So it's 0.303. So if you were to do it at 20 milliseconds, I would be 0.303. This is again, yeah, at 0.303 amps, because this is only 25 volts, 25 ohms up here. So that's basically that 0.303 amps. All right. So now I'm grappling with what to do with the rest of the circuit. All right. So at this point in time, I say, okay, at a certain point in time, I is equal to 0.303 amps. And then what do you do with the rest of the circuit? You basically say, I've got my 12 volts, I've got my 25 up here, and I've got my thing down here with the L. This is my L, which is 500 millihenries. And I've now got a value of I is equal to 0.303. Now, it determines everything else. So what's 0.303 times 25? 7.57. So now I can go back and I can say at that instant in time, I've got 12 volts over here. I've got 7.57 volts over here. And I have what's left over here. What's left? What is this if this and this are known? It's what's left. It's 12 minus 7.57, right? Or what? Does everybody see that? So this is 4.43. At that instant in time, you take a picture and you're going to see those voltages. So what did you do first? Who leads? Who's the leader of the band? Who conducts? Who's the conductor? In a capacitive circuit, it's voltage. In an inductive circuit, it's current. Okay, so the leader of the band is the I, and then everything else follows. That's it. I know coming back from a vacation on a cold, stormy day like today, you don't like to, think that much, but this is how it's done. This is how you start thinking through these problems. You lead with what is absolute, and the absolute is I. Everything else follows. Any questions? Will this be on a test? Yes, this is the kind of stuff you ask on a test. Yeah. Okay, so does everybody follow that? You lead with the current in an inductive circuit. You lead with a voltage in a capacitive circuit, and then everything else follows. Okay, so why do you lead with current? Because of Eli. Okay. All right, number 18, same thing, same song, second verse there, and then 19 and 20. Now, what else can I do to make this more complicated? Well, I can do this. This is the same thing, only here we have both. This is the same thing we had with capacitive circuits, except now this is an inductive circuit, okay? So here in 21, it asks for the time constant in switch 1, and then you switch to position 2, and then what would be the time constant? So I'm just going to do it both ways. 21 is, now you got 30 volts, and you've got a more complicated circuit, but it's really not. It's two circuits. You got the switch either here or the switch down there. So basically I'm going to do this. I'm just going to draw it like it's just in position 1. Okay, it's position 1. And I've got 30 volts, and I've got 10K, and I've got 400 microhenries. All right. What is the equation that you can write? I is equal to V over R, 30 over 10K, 1 minus E, because it's a charging circuit, 1 minus E to the minus T over tau, where tau is equal to L over R. All right? What is L? 400 times 10 to the minus 6th. R is 10 to the 4th. So, what would be tau? What is tau? 400 times 10 to the minus 10th. Quick. Okay, so does that make sense? Questions about that? So then it asks the question, what would be, that's the time constant, and that's the equation for charging. What would be for discharging? Well, this is for discharging. Okay. Now you have to understand that it only works if this thing was charged up to its final value. What would be the final value of this I here? So this I is going like this, like crazy. It's 20K over here, and you've got an L of 400 microhenries over here. Now, everybody's seen a flywheel, or you've seen basically just something that like a free spinning tire. Okay, this is a free spinning tire. You can't stop that thing instantaneously. You could turn all the power supply off to it and everything, but you cannot stop it immediately. So what's it going to do? It's going to continue spinning until it dies, until it stops, and that's what's going to happen here. So this is going to be a circuit of what? What is the initial value of I? In this circuit, it's going to be what? It's going to be this 30 over 10K, or what? 3 milliamps. So my initial condition here is the same as my I up here, okay? So these are equal. Only if you say, let it go to its final state. In other words, let this thing just go for a while like this. And let it get full steam. Let it get fully on. And then you flip it to this position, then what's going to happen? Well, what actually happens is this thing just keeps going until it dies. Excuse me, this one here, until it dies. All right? It goes until it just kind of decays down. And how do you write that? I here is equal to V over R, or 3 milliamps, E to the minus T over tau, where tau now is equal to what? L, 400 times 10 to the minus 6 over what? 20K, which is what? Bigger resistance, so it's faster. So it's going to charge up. It's going to charge up faster. No, excuse me, it's going to charge up slower, and then it's going to decay faster, because why? Because of this R in the denominator. The R being bigger it's going to go down faster, okay? Any questions about that? Now, this one's a little tricky, because why? Well, in position 1, this is my R, but in position 2, this and this add together to be my R. Everybody follow that? So here, you charge with this, and then when you discharge, the R is this plus this. It's the only difference. And this one is a little different, because in this one, your R for your charging is this, and your charging for discharge is just this one right here. So if you say, what is your charging R? It would be this plus this. My discharging R is just this. And you come down to this one, and now what do you have to do here in 29? What do you have to do in 29? It's different than before. Why do we talk about Thevenin so much? Why do we talk about Thevenin so much? Because this is not in its Thevenin equivalent form, is it? We've got to make sure that before we do this, we do what? Thevenize. Okay, so here, in order to find the equations, you have to find the Thevenin equivalent of this, which is the same thing we did with capacitors. This is the exact same circuit, maybe even the same circuit as we did with capacitors. But here, you have to Thevenize. And how do you do that? Okay, so number 29, you have 60 volts, and then 3K up here, and then 6K down here, and then cut the circuit right like that, all right? Now, what is V Thevenin? It's voltage divider, 6 over 3 plus 6 times 60, or what? 40, right? What's R Thevenin? Everybody agree with that? You want to vote on it? Does everybody follow what I just did? I'm converting this circuit into this circuit. Because this is what we have to have in order to get this to work. In order to do that, you have to Thevenize, okay? Thevenize everything before your eyes, Thevenize. That's why God made your eyes to Thevenize. Not really. But it says, I can't get anybody to smile at all today. It's kind of like, maybe a couple of you, but days, huh? There's a smile. See a couple. All right, so why do we have to do that? It's force fitting it into a circuit that we know the answer to, right? And the only way to force fit it in is to Thevenize it. That makes sense? Because we know how to solve this problem, we do not know how to solve this problem. So you force fit it into this. In order to do that, you have to Thevenize. Follow the rules. You basically take your scissors and you cut the circuit right there. All right? Now you can ignore this part because why? Because the switch is not in that position. The switch is in the one position. So you can basically snip, snip, done. And now you've got this. So V Thevenin is easy. 6 over 3 plus 6, 60 is 40. What's R Thevenin? Well, you start here and you walk back. And what do? You walk through the 3K. You start at the point of here. You walk through and you can either go one way or the other. And what do you do with the voltage supply? Do you open it or short it? You short it. Voltage supplies you short, current supplies you open. And now you've got 3K and you got 6K. Do I have a choice? Can I go this way or go this way? Yes, you can go one way or the other. So it's a parallel circuit. It's a parallel circuit. So now you can say 6K in parallel with 3K is equal to 2K. So I can now go back up here and write 40 and 2K and solve, and I'm done. So I is equal to 40 divided by 2K times 1 minus e to the minus t over tau, where tau is equal to L, 5 millihenries, over R, or 2K. Everybody see that? That's how you solve it. All right, now let me see what I assigned as problems, because I think I assigned that was a problem. I'm not sure. So, if you are, I don't think anybody's handed in any assignments yet, but in chapter 8, I say today you have 24 and 25 on page 291 to hand in, and on whatever, I say 11, 12, 29, and 30. So I just solved 29. I think I've solved 11 and 12, 29 and 30. So those are due, what's today, the 20th? Those are due on Thursday. So you should have those handed in. And again, I do not take off for lateness handing of papers in, but please hand them in because they are due on those days, and I got too many things to do to say, well, you were 1 day late or you're 2 days late, and but by the first test, you have to hand everything in that's due. So you have to hand them in. And some of you are procrastinators, I know that, but I work every problem in this course pretty much for you already. So you don't have to, you can just take what I give you and write it and be done with it, right? You can just rewrite it. But that's not the goal of this course. The goal of this course is for you to work these problems yourself. So if you can work these problems yourself and then look at my solution and say, oh, yeah, I got it right, or he got it wrong, or whatever, you know, that's the goal. And I'm not trying to set you up for anything. I'm just trying to tell you that that's how you learn. And if you don't do that, come test time, you don't get you get a cheat sheet, but you don't get, the 10 videos. You don't get everything else. You have to do it yourself. So at that point in time, it's a little bit more inclusive that this stuff. So again, I'm not trying to push you. We're not trying to intimidate you. I just want you to understand that you do have to work these problems yourself. You have to just sit down and work these problems, at least to a point, yourself. I don't grade off I just look at the problem and say, okay, you did them. I don't grade off on them. I don't try to go through and see, did you do the right thing? Because I don't have time. I do say, yes, you did them, no, you didn't, and hand them in, and then I hand them back to you. That's it. And it sounds cheap, but sometimes people grade every homework assignment, and to a great extent, they go really in depth. Oh, you didn't do this quite right or that quite right. I don't have time. But I do know that if you hand them in, the act of handing them in and having worked through them is a step, but it's not the only step. You can copy them from somebody else, and it means nothing to you. If you don't work them yourself, at least understand them yourself, you're getting no benefit from them. So the benefit comes from working them, trying them, listening to the videos, listening to me, trying to explain them, go over them, that type of thing. And I can mess them up with the best of them. But basically, I got the right ideas. I've taught this enough times, and, I know where the basic troubleshooting is. And we got to get this DC side straight, and then we go to the AC side. And then you've got both of those pretty well mastered. And then we go and have a little bit of fun at the end of the course. This is not a 15-week course. I'll get you through the AC side of this in 2 weeks. What? You're going to teach a 15-week course in 2 weeks? Pretty much. Yeah. Once you get this down in the AC or in the DC side, and you can find V equals IR, and then you can find Thevenin, it seems like the rest of it is pretty straightforward. And you get a calculator that you feel comfortable with, that you can manage to get through all this imaginary number stuff. We, in the olden days, had to sit there with a slide rule and do these. And you say, what is a slide rule? If you ever come back to my office, I'll show you what a slide rule is. Okay, but that was in the days before, that was when the dinosaurs were still walking around. I graduated in 1971, in the spring of 71 from college, and that was the last semester that basically they had not moved to calculators yet. Now, there were a few calculators out there, and they cost $400, and you could throw them against a wall and they wouldn't break. But they were really clunky. But the first calculators were really coming in the fall of 70, in the spring of 71, and that's when the first calculators actually hit. Up until then, everything was done with, as they call them, slipsticks. And it's sine, cosine, going back and forth and 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 back and forth. And the number 3 significant figures, 3 sig figs. Everything had to be done to 3 sig figs. What is a sig fig? Significant figures. Because you had to read and interpolate all these numbers on the slide rule. Yeah. Not fun, but that's what we did. And when I saw the calculators that we got now and the capability that they've got, you just knock it in the head in about two seconds, whereas we took an inordinate amount of time to find one answer. And I kid you not, if you missed one little thing, it was off to this, it was done. But again, I'm not trying to make you feel like it's less than today, because this stupid little $20 calculator is so beneficial to you, and it will get you through so many of these things without having to, crank through that old stuff. And I don't want you to have to go back and do that. No way. But again, Get the main important things, get on with your life, do the other stuff, understand why we're doing this. Uh, one of the big reasons why we're doing this stuff is because you get good at problem solving. Whether it's this problem or whatever, you can throw yourself into a problem and you won't give up. And this ability to not give up is extremely important because you're not going to, I can't prepare you for the problems you're going to solve outside of here. No way. I'm not going to even try. I can say, well, you did this problem, this problem, this problem, this problem, this problem, and they'll hire you. Whether or not you want to work for that company or not is up to you and them and whatever. But there are people that will hire you if you can work problems like these, believe it or not, and they trust that you can work the problems that they have to do, but they will not be the same problems. I don't disappoint you, but they won't be the same problems. Some of the understanding you get in this course, you will use, and I'll bring that out. I'll show you some of the things that you can get, why certain things work the way they did. And I just explained to you today, as you turn a spigot on, or and drain something out, you actually see that exponential decay. You see it in the real world. It's there, and you just don't. What is that? What's an exponential decay? Okay, there's my e to the minus t over tau. What's the tau of that? What's the tau of that thing draining down? Well, when it goes 63% down, that's 1 tau. So you get 1 tau when it goes 63% of the way down. So you measure it when it goes from up here to there, 63% of the way, that's 1 tau. And that's exactly it. That's exactly it. Okay, and 5 tau, it'll be 99% done. All right? Some things are exactly that way. I'm rambling, but I'm going to quit. But basically, anybody have any questions? No? Take care. See ya. Hand your homework in, and we'll see you on Thursday ready for a lab. Okay?